Okay, we're going to talk about how to do some of the calculations with looking at heating curves and cooling curves. So a heating curve tells us where our temperature change occurs for phase change. So if we look at the graph, we have temperature along the y-axis and the amount of heat added to our system along the x-axis. So imagine starting with a solid of water at minus 40 degrees. So we have a block of ice, minus 40 degrees Celsius. As we add heat to our block of ice, we're going to notice that the temperature starts to increase. So that heat is going to increase the kinetic energy of the solid molecules, allowing them to vibrate more and shake more within their lattice. This increase in kinetic energy is reflected as a temperature increase. So we see the temperature increasing as we add our heat up until we get to 0 degrees Celsius. At this point, water starts undergoing the phase change from solid to liquid. So any heat that's added is no longer increasing kinetic energy, but is going to separate those intermolecular forces, loosening up the solid molecules so that they separate enough to become liquid molecules. Alright, so along this flat line where we don't see any change in temperature, we're loosening up those intermolecular forces, turning all of our solid molecules into liquid molecules. Alright, so this would be our fusion or melting. Then, once all of our solid molecules are liquid, we can then start increasing kinetic energy again for our molecules. So adding more heat causes an increase in kinetic energy and therefore an increase in temperature of the liquid until we get to 100 degrees Celsius. At 100 degrees Celsius, liquid water starts vaporizing into gas. So any added heat no longer increases kinetic energy, but starts loosening up those intermolecular forces even more so that we are creating gas molecules. And remember, to vaporize takes a lot more energy because none of the gas molecules will be interacting anymore. So we're getting rid of all the intermolecular forces. So our temperature remains constant as kinetic energy is constant until all of our liquid molecules are gas. This would then represent the boiling point for water. Then once all our molecules in their gas phase, any extra heat that we add simply increases the kinetic energy and therefore the temperature of the substance. And so we just see the temperature going up. So this kind of heating curve tells us two very important temperatures, the melting or fusion temperature, as well as the vaporization or boiling temperature. It can also tell us a few other things if it's drawn to scale. So if we imagine that this graph is drawn to scale, even though we don't have a scale down here, and we imagine that we're looking at 1 mole of water, the length of these flat lines would represent our delta H values. Okay, so the length of this first melting or fusion line would indicate the delta H of fusion. The length of this boiling line would indicate the delta H of vaporization. So notice how the delta H of vaporization is much greater than the delta H of fusion. Alright, if we also imagine this is our 1 mole of water, and this is drawn to scale, our diagonal lines would also represent a heat capacity value for each of the phases. So the slope of our line would represent heat capacity for a solid until we get to the melting point. This line would represent our heat capacity as a liquid, and then our heat capacity as a gas. So we're going to use this idea to look at the math for finding how much heat is required to go through a heating curve, or how much heat is released when we have a cooling curve. Alright, so we're going to break this down into 2 stages. The first stage is going to be if we're within a phase, if it stays a solid or stays a liquid or stays a gas, and we're on one of those diagonal lines on the graph, we're going to use a familiar equation. Q equals mCp delta T, where Q is our heat required or heat released, M is the amount that we have, whether in moles or grams, Cp is our heat capacity for that phase, and delta T is our change in temperature. Alright, the second type of equation we're going to use has to do with our phase change. If we're changing from solid to liquid or liquid to gas, we need a different equation. We need to incorporate the delta H values. So for fusion, we have Q is equal to M, or moles or grams, times delta H of fusion. If we're doing liquid to gas, Q is equal to M, moles or grams, times delta H of vaporization. We want to calculate Q for each of these steps, or each of these stages, and then using Hess's law, we can add all of our Q values up to get a total heat requirement, or total amount of heat released, if we're looking at a cooling curve. So remember, Hess's law says that this is a state function. It only matters where you start and where you end, and it doesn't matter what path you take when we're looking at enthalpy. Alright, so we're going to break this down into different phases, or different states. So we can work within the solid phase. So we'd have our Q is equal to M times heat capacity times delta T. We then have a phase change. Q is equal to M times delta H, in this case fusion. Then we have another phase where we have Q is equal to M times Cp times delta T. Then phase change, vaporization. Then within the gas phase, we're going back to our Q is equal to M times Cp times delta T. So let's look at an example with water. And this is a cooling curve. So you'll notice it goes the opposite direction. Instead of starting with a solid and going to a gas, we're going to start with a gas and go to a solid. The idea is the same. We want to break it into the different stages. So if we're starting with a gas at 130 degrees Celsius, the first thing we have to do is cool down the gas. So heat is going to be released, kinetic energy decreases, temperature decreases. Then we'll have our phase change from gas to liquid using our delta H of vaporization, or rather the negative delta H of vaporization. Then our stage 3 is cooling the liquid. Alright, then we have our phase change, negative delta H of fusion, until we get to solid, and then our last stage is cooling down the solid. So let's look at the calculation. For the first stage, we're starting at 130 degrees Celsius, and we can only cool the gas down to 100 degrees Celsius because this is the boiling point of water. So we're working with 2.5 moles of gas at 130 degrees Celsius, and we want to cool it down all the way to -40. So here's our first step. Turning the gas from 130 to 100 degrees. So cooling the gas as low as it will go. So Q is equal to 2.5 moles, that's our M, times our heat capacity. This is a constant value. You'd be given constant values. You do not have to memorize them. And then times our delta T, which is final minus initial. Final temperature is 100 for this step, beginning at 130. Alright, so this is where our negative value comes in. Alright, so we have Q is equal to minus 2,482 joules, or negative 2.48 kilojoules. Just for that first step, this is the heat that is released. Alright, step 2 is our phase change. We got to turn all of that gas that's at 100 degrees into liquid at 100 degrees. So this is our second type of equation, where we have our amount, 2.5 moles, times our negative delta H, or vaporization value. And again, this is a constant value you'd be given. So our negative value for this step comes from the delta H, because we're not vaporizing, we're condensing. Alright, so we have negative 102 kilojoules for the second step. Alright, after we've turned all our gas into liquid, now we're going to cool down the liquid from 100 down to 0 degrees Celsius. So we go back to our first type of equation. Q is equal to 2.5 moles times our heat capacity in the liquid phase times our temperature change, final minus initial, to give us negative 18.9 kilojoules just for cooling down the liquid. Alright, step 4, once we've cooled our liquid, now we're going to undergo the second phase change from liquid to solid, staying at 0 degrees Celsius. So 2.5 moles times our negative delta H of fusion, because we're not melting, we're freezing, gives us negative 15.0 kilojoules. Alright, and then our last step, water in the solid state at 0 degrees Celsius, we want to cool it down to minus 40. So we're working within a phase, so we have 2.5 moles times our heat capacity of a solid times our temperature change, final minus initial, for this step, to give us negative 3.76 kilojoules. Alright, so we had 5 steps in this problem because we started with a gas and we wanted to go all the way to a solid. So then we're going to add up all 5 Q values. Notice that they're all negative. So if we're doing a cooling curve, all of your Q's will be negative, as heat is released at every single step. If you're doing a heating curve, all your Q values would be positive, as you're increasing heat at every step. So make sure you pay attention to that. Alright, so we have 5 negative values adding up to our total Q requirement for the amount of heat released in order to turn our gas into solid. Alright, so a couple of key points to make for this. Heat change within a phase is changing the kinetic energy within the molecules, and it results in a temperature change. Phase change, we have constant temperature because our kinetic energy is not changing. That heat is being used to loosen up intermolecular forces in order to change the phase. Heat capacities are going to be different for every substance and every phase. So these are constant values you will be given for the problem. Make sure you know what phase you're working in. And then Hess's law allows us to add all of these Q values for every stage together to create the total Q value for either heat needed or heat released from a problem. Alright, this is the end of the concept for using the different stages to calculate your Q. There's a second example with ethanol in a next video. Thank you.